In this video, I am going to discuss about the rubber, how rubber is used and where the rubber are used in aircraft, and it is the material of the aircraft to be used where. Now come, rubber is used to prevent the entrance of dirt, water or air, and to prevent the loss of fluids, gases or air. It is also used to absorb vibration, reduce noise and cushion impact loads. The term rubber is as all-inclusive as the term metal. It is used to include not only natural rubber but all synthetic and silicone rubbers. Now, natural rubber. Natural rubber has better processing and physical properties than synthetic or silicone rubber. These properties include flexibility, elasticity, tensile strength, low heat buildup due to flexing (hysteresis). Natural rubber is a general purpose product. However, its suitability for aircraft use is somewhat limited because of its inferior resistance to most influences that cause deteriorations. Although it provides an excellent seal for many applications, it swells and often softens in all aircraft fuels and in many solvents naphthas, etc. Natural rubber deteriorates more rapidly than synthetic rubber. It is used as a sealing material for water/methanol systems. Now, synthetic rubber. Synthetic rubber is available in several types, each of which is compounded of different materials to give the desired properties. The most widely used are the butyls, bunas, and neoprene. Butyl is a hydrocarbon rubber with superior resistance to gas permeation. It is also resistant to deterioration. However, its comparative physical properties are significantly less than those of natural rubber. Butyl will resist oxygen, vegetable oils, animal fats, alkalis, ozone, and weathering. Like natural rubber, butyl will swell in petroleum or coal tar solvents. It has a low water absorption rate and good resistance to heat and low temperature. Depending on the grade, it is suitable for use in temperature ranging from -65°F to 300°F. Butyl is used with phosphate, ester, hydraulic fluids (Skydrol), silicone fluids, gases, ketones, and acetones. Buna S rubber resembles natural rubber both in processing and performance characteristics. Buna S is a water resistant as natural rubber but has somewhat better aging characteristic. It has good resistance to heat but only in the absence of severe flexing. Generally, Buna S has poor resistance to gasoline, while concentrated acid and solvents. Buna S is normally used for tires and tubes as a substitute for natural rubber. Buna N is outstanding in its resistance to hydrocarbons and other solvents. However, it has poor resistance in solvents as low temperature. Buna N compounds have good resistance to temperatures up to 300°F and may be procured for low temperature application down to -75°F. Buna N has fair tear, sunlight, and ozone resistance. It has good abrasion resistance and good breakaway properties when used in contact with metal. When used as a seal on a hydraulic piston, it will not stick to the cylinder wall. Buna N is used for oil and gasoline hose tank linings, gaskets, and seals. Neoprene can take more punishment than natural rubber and has better low temperature characteristic. It possesses exceptional resistance to ozone, sunlight, heat, and aging. Neoprene looks and feels like rubber. Neoprene, however, is less like rubber in some of its characteristics than butyl or buna. The physical characteristics of neoprene, such as tensile strength and elongation, are not equal to natural rubber but do have a definite similarity. Its tear resistance as well as its abrasion resistance is slightly less than that of natural rubber. Although its distortion recovery is complete, it is not as rapid as natural rubber. Neoprene has superior resistance to oil, although it is good material for use in non-aromatic gasoline systems. It has poor resistance to aromatic gasoline. Neoprene is used primarily for weather seals, window panels, bumper pads, oil-resistant hose, and carburetor diaphragms. It is also recommended for use with freons and silicate ester lubricants. Thiocol, known as the polysulfide rubber, has the highest resistance to deterioration but ranks the lowest in physical properties. Thiocol is not seriously affected by petroleum, hydrocarbon, esters, alcohols, gasoline, or water. Thiocols are ranked low in such physical properties as compression set, tensile strength, elasticity, and tear abrasion resistance. Thiocol is used for oil hose, tank linings for aromatic aviation, gasolines, gaskets, and sails. Silicon rubbers are a group of plastic rubber materials made from silicon, oxygen, hydrogen, and carbon. The silicons have excellent heat stability and very low temperatures flexibility. They are suitable for gaskets, seals, or other applications where elevated temperature up to 600 degree Fahrenheit are prevalent. Silicon rubbers are also resistant to temperature down to minus 150 degree Fahrenheit. Throughout this temperature range, silicon rubber remains extremely flexible and useful with no hardness or gumminess. Although this material has good resistance to oils, it reacts unfavorably to both aromatic and non-aromatic gasolines. Silastic, one of the best known silicons, is used to insulate electrical and electronic equipment. Because of its dielectric properties over a wide range of temperature, it remains flexible and free from creasing and cracking. Silastic is also used for gaskets and seals in certain oil systems.